Earthquakes, like mountain formation, occur because of stress that builds up in the crust. When stress causes the crust to fold, earthquakes generally do not occur. When the Earth is folding, it is bending to the stress and does not store potential energy. This kind of deformation is called plastic deformation. However, when the crust stretches and stores potential energy, called elastic deformation, we can experience earthquakes. Rock can only stretch so far before it breaks, so eventually it faults, releasing the energy that it had stored, and returns to a less stressed position, a movement called elastic rebound. The energy radiating out from the fault moves through the ground in waves and causes it to shake. This is an earthquake. Looking at the diagram, we can see that stress builds from A to B, causing the ground to deform. As it deforms, it stores energy. In C, the ground faults and the energy releases, causing an earthquake. By D, the energy has been released and the ground rebounds to an unstressed, undeformed position. In the diagram, the earthquake was taking place around a strike-slip fault, but any type of faulting can cause an earthquake. Usually, faults and resulting earthquakes occur near tectonic boundaries because they tend to build up stress faster than areas in the middle of tectonic plates. As mentioned earlier, the shear around transform boundaries usually causes strike-slip faults. The compression around convergent boundaries causes reverse faults, and the tension around divergent boundaries causes normal faults, either at the surface or far beneath the ground. They can occur in the middle of tectonic plates if stress can accumulate. However, this does not happen as frequently as near boundaries, and these earthquakes usually do not have the same intensity as those near boundaries. First of these two diagrams shows the occurrence of earthquakes and volcanic activity around the world. The second diagram shows Earth's tectonic boundaries. In looking at these two diagrams, it becomes clear that the occurrence of earthquakes and volcanic activity tends to coincide with the position of tectonic boundaries. Some seismic activity does occur away from boundaries, but this activity is far and away in the minority. The energy that causes an earthquake originates as a sudden release of kinetic energy during elastic rebound, from the potential energy stored in Earth stressed by plate tectonics. However, the actual effects of the earthquake, the actual shaking felt, occur because that energy continues to move out from the focus in waves. These waves of radiating energy through the Earth are called seismic waves. There are two main types of seismic wave, differentiated by where the wave travels through the Earth. A wave that travels through the Earth's interior is called a body wave. Since the Earth's interior is denser than its surface, these waves travel the fastest. The fastest body waves are called P waves for pressure or primary waves. The two possible names help describe this type of wave. P waves are longitudinal, which means that they shift matter forwards and back in the direction that the energy is traveling. Essentially, each wave is an alternating series of increases and decreases in pressure, thus the name pressure waves. Since the energy and matter are all moving in the same direction, they're also the fastest waves, and the first ones that can be measured, thus the name primary waves. These are the only waves that can move through the fluid layers of the Earth. Comparatively, the other type of body waves, S waves, can only move through solid rock. S waves are called shear waves or secondary waves because they exert shearing stress on the rock, causing it to move from side to side, and because they come second behind the primary waves. S waves are an example of a transverse wave, meaning that they cause matter to vibrate perpendicularly to the direction that the energy is traveling. The other main type of seismic wave, surface waves, and its two subgroups, are also examples of transverse waves. Surface waves travel through the upper few kilometers of Earth's surface and, because they move slower than body waves, can be much more destructive. If a surface wave causes the ground to vibrate up and down, it is called a Rayleigh wave, and if it causes the ground to shift from side to side, then it's called a Love wave. Any earthquake has both body and surface waves, and usually all four subtypes emanating from the focus simultaneously. But because of the different ways that the waves move and variable composition of the Earth's crust, how we experience an earthquake on the surface can vary significantly from place to place. Some earthquakes are difficult to ignore and can be felt for thousands of miles, but others are subtle and can't be felt without special instruments. The instruments used to measure seismic waves are called seismographs. These have gotten more complex and much more sensitive with the advancement of technology, but in their simplest form, they're just a needle or writing utensil that is capable of moving independently of the ground beneath it, and with enough inertia to remain still. When the ground moves, the entire machine moves, but the needle is able to remain still. A paper called a seismogram is beneath it and moves with the earth. When it moves, beneath the stationary needle, the needle traces the vibrations on the seismogram and gives information about the wave's energy causing the earthquake. By comparing multiple seismograms recorded at different locations, scientists can use the intensity of the vibrations at each location to work backwards and determine when and where the earthquake originated. The point inside of the earth where an earthquake originates is called the focus. This is the point in the crust where the rock faulted or an existing fault shifted again. Usually the focus is well beneath the Earth's surface, though. The point on the surface of the Earth, directly above the focus, where the earthquake is felt most severely, is called the epicenter. The strength of an earthquake is called its magnitude, and is measured on the Richter scale. Usually, this corresponds to how much it is felt at a particular area, but that isn't the focus of the particular measurement. Instead, the magnitude is measured by looking at raw ground movement. Different levels of ground movement are given different number values, each number value being 10 times as much as the last. The ground of a 4.0 earthquake moves 10 times as much as a 3.0, and likewise a 5.0 moves 10 times as much as a 4.0. Jumping from a 5.0 to a 7.0 would mean the ground is moving 100 times as much. How much an earthquake is actually felt at the surface of the Earth, and how much damage it actually does, is called its intensity, and is measured on the modified Mercalli scale, or MMI. This varies from location to location based on how the earthquake's waves interact with the rock or soil substrate beneath each location. The closer to the epicenter a place is, the more intense the earthquake is likely to feel. The scale is denoted by Roman numerals, with a 1 meaning not felt at all, and a 12 meaning total devastation of the area. The earthquake that hit Haiti in 2010 was a 7.0 on the Richter scale, and its intensity reached levels as high as 10 on the MMI scale. By comparison, the earthquake that hit San Francisco in 1989 was also a 7 on the Richter scale, but its intensity peaked at 8. Why the different intensities for the same magnitude earthquake? One reason that the earthquakes were felt differently and caused different degrees of damage is the composition of the rock substrate beneath each location. Haiti is primarily composed of loose sand, meaning it has a lot of room to move if a wave of energy passes through it. Parts of California also have sandy substrates, but not to the extent of the Caribbean islands. Another reason is the infrastructure of the communities. Haiti is considered a developing nation, making it economically a very different place from the U.S. Most of the buildings and houses in Haiti had no foundation, and many were just pieced together from wood, chicken wire, and other scrap available. Such construction was very vulnerable to the ground moving beneath it. San Francisco is a major metropolitan area with a history of seismic activity in a developed nation. Most of its buildings had been constructed with earthquakes in mind, so they were much better prepared to withstand the ground moving beneath them. Taken together, a wide range of factors can influence the intensity with which an earthquake is felt in a particular area. If you think back, there have been several earthquakes in the Northeast in recent years. But have you felt all of them? Do you know people living nearby who experience them differently than you?